Hi, I'm Lachlan. I work here at Tubals, one of the engineers. I do things occasionally. In this talk, I'll be talking about a project we worked on called the Wayo project. Wayo was a project that came to us from a client who was in Hunters and Collectors. I won't say his name, he doesn't like the publicity either. He came to us looking to basically build an application that required more effort for a child to actually interact with it. He was sick of watching his grandchildren look at a phone, watch a YouTube video and do nothing. So we wanted to come up with something that allowed them to actually interact with the phone. What he came up with was face tracking that would then envelope the child in something along the lines of a story. The first IP we got was the Wiggles. So we started building for that, and basically what it would do is face track, put a mask of one of the Wiggles characters on you, and you would sing a song along with that. So we started building this, eventually got to a point where it wasn't running fast enough. So we had to decide, how do we want to do this and why do we need to go parallel? But first of all, we want to talk about how did we achieve 1 week of multi-threading without any issues? We used Rust. Fearless concurrency, what more could you want? Any questions? Very good. Moving on. Firstly, why did we need to go parallel? There was actually quite a few components that went into the application. So this is all happening in the Rust core library, but we're also building this for iOS and Android. So we need a cross-platform approach to be able to handle this. A lot of things need to happen. We need a runtime, which is actually running the experience. The experience we made was built off JSON files that we called EDL files. Event-driven lists, I believe it stands for, but doesn't matter anymore. So it's basically just event blocks that describe what we're actually showing to the user as we're running the experience. So the runtime has to handle looking ahead, building these events as they're going, making sure we're doing it in real time and showing it to the client at the good speed it needs to be. Second up was rendering. We were using Vulkan as our renderer. So we decided on Vulkan, new language. It allowed us to get rid of shit Android devices because boy, is there a lot of those, as we found out. So we were able to kind of have a nice little lower limit to what we're able to actually show. Next up was asset loading. We had a lot of 3D assets. We had a lot of MP4s. We had a lot of audio files. We need to be actually able to load those from storage on the device, show that to the user, decode it, all that fun stuff. We needed graphs for the event. Nathaniel came up with a great idea of using graphs as our actual things for the event. So for example, if we have an event that is just showing the video, we just have a video clip event. That video clip event then is a graph that builds out all the required systems it needs. So it needs to build the decoder, needs to build the asset loader, it needs to build the actual rendering of that planar image to the device. All these things need to happen, and they need to happen quickly. You also don't want them to be these kind of free-form things. So the graph idea came up nicely because it was a nice little condensed thing to do. We also had face tracking. So the face tracking was based off a cascade approach using a library known as Pico. We'll get into that a bit later. And the last thing was decoding video and audio. So that was a big one, especially since we're on mobile devices. We can't just throw FFmpeg at it, and it's not going to do it quickly enough. So we had to figure out things for all these. All of these needed to run at the same time, and our time limit was 40 milliseconds. 25 frames a second is pretty much how movies work. We wanted to make it good. So we had 40 milliseconds to do all of the above 25 times a second. Can't really do it sequentially. We tried, didn't work well. The first step was we were running it with just cargo run, debug build. It's quite slow. The amount of times we had people come to us and go, it doesn't run. Like, well, did you run it with the release tag? And they're like, oh, maybe. That figured itself out pretty quickly. So yeah, that was the biggest first step there. So first, we have to make it asynchronous. So the first thing we did, this was back in 2019, so we didn't have any of those nice little async await beautiful stuff that we could have had. Instead, we had the Tokyo runtime. So Nathaniel, while he was in a hospital bed with tonsillitis, pretty much tonsillitis, right, Nathaniel? No? Something like that. High as a kite on morphine, pushed this to the repo. Basically what happened was we needed to take these graphs, which were, this is currently being built completely sequentially. So if you start the event, first of all, we have to decode a bunch of audio, a bunch of media. We then have camera frames we have to collect. We also have to collect the face tracking data. All of this is happening sequentially. And obviously you're going to run into some issues if you get a big graph that needs to be built, because as you can see, we have this just build event that's just happening in a for loop. Eventually it's going to crack its stuff. So what we had to do was add in the Tokyo runtime and make this an asynchronous thing. So the first thing we did was, all we had to do was create these futures. So we created a future builder, and that would actually go through and build the event and then spawn that on the Tokyo runtime as a submit task. What that would do is then take the submit task, run it in its own thread managed by Tokyo, and be able to support a future that would come back. And now you have your asynchronous runtime going quite nicely. The first thing we hit with the compiler, and boy was the compiler beautiful for this, was this: the trait std marker send is not implemented for X. You will hit this every single time you try and do anything asynchronous. Basically, this is just the compiler saying, the thing you're trying to move across a thread, we haven't set it up to be moved across a thread, so you're shit out of luck. Thankfully, we have a few ways we can get around that that don't break the compiler, are actually safe, and the compiler will tell you you're doing it correctly or not. So the first thing we did was we had the future item from futures RS. So that came through, and basically you're able to take that future, allow it to have an arced up evaluator. And what this did was, the arc is an asynchronous reference count. So instead of having to deal with just your sequential reference count, the asynchronous one allowed it to be stored across threads. You're able to clone the internal contents and share that. And as long as everything within that content is safe to be mutable across threads, everything should be fine. The second thing we had to do was then throw that on the heap. So we box that up and we just tell it to apply a send and hope everything works. Sometimes the compiler is not too happy about that, so you have to resort to more drastic measures. The drastic measures in this case being a mutex. Mutexes come very handy across all these threads we were running, especially, for example, these are the active graphs, so graphs that are running at this moment in time and will continue running for this event block. The mutex allows it to basically just be shown across threads, and we make sure that things aren't getting written unless they've been read, and everything happens sequentially in that regard. It doesn't have to happen sequentially, but I think we did it that way to be nice. Hi, Elfie. Elfie asked, did we hit performance issues with the mutex? Yes, not only performance issues, we also hit a runtime issue that the compiler wasn't able to catch. We ended up locking ourselves with a mutex, pure deadlock where something was trying to write to it, something was trying to read from it, and that happened. So basically, the compiler won't protect you from a mutex deadlock. So that's a pretty big thing. We expect Rust to pretty much catch everything. It can't be that smart, unfortunately. Mutexes are still very much human error, so you have to try your best. I didn't do very well in that regard, as we'll see later, because I hit too many mutex locks for it to be funny anymore. And I remember James just sitting at my desk fixing that for me. So that was pretty interesting. So yeah, performance issues started off as a thing mostly due to the deadlocks. Eventually, we managed to make the system a lot more flexible around the mutexes, where we split the mutexes across different events, so it wasn't sharing the exact same thing. That required less waiting for the read, waiting for the write. So that helped out quite a lot in that regard. And then the next thing that helped us making our things thread safety was the atomic usize, or the atomic types. Atomic basically just means it is happening sequentially no matter what, and allows it to be thread safe in that regard. So the atomic usize, instead of just the usize type, can be shared across threads. You can make sure that it is loaded sequentially if you like it. You get to choose the ordering that these things happen in, and basically just makes that struct, or this, in this case, the struct, completely safe across threads in that regard. So atomics, very, very useful if you're doing things across threads. quite quick as well. They are basically a mutex, but they're actually cooler because the compiler knows what to do with them rather than just a mutex around arbitrary data. And then finally, we did a lot of FFI because we had to hook into the C libraries of iOS and Android. So while it doesn't look like it should be done, you can do it and it just works. Adding an unsafe implementation of send and sync, which is required by threads to actually be threadable. We were able to add these to our C types. So for example, with Android, we just have a pointer that refers to the Android media decoder. And we can tell that on the Android side, that Android media decoder is just running as its own little pointer in its own little loop that's in the C runtime. We can just tell Rust, we know it's fine. That's why it's unsafe, because we're telling the compiler to trust us, which it never should. So just adding this, eventually everything just worked out perfectly fine. As long as on the other side of the loop or the other side of the runtime, everything's fine and it's not doing some crazy magic, you're okay. So this obviously made it that we had to update our core loop. So you can see we took these graphs, spawned a bunch of them and submitted them. That submit then has to go through into our core loop, which basically played through the entire EDL or the event blocks. You can see here, you don't have to read it, it's fine. I just put it there because it's pretty and it's better to talk with something in the background. So you can see we have a few states. We've got our preparing, which is just kind of waiting for all the graphs to be initialized for this current frame. Next step was it being actually prepared. So we're just telling it that things are happening. And then we have playing, which is basically telling us that we look at what the current frame is, we look at the frame that this event block is meant to end, and we just say, the graphs are built, it'll be fine, we go from there. A lot of other things are happening behind the scenes, but basically this is the core loop that is just sending back asynchronous info to the Tokyo runtime and telling it, go ahead, don't go ahead, wait, everything's fine. And yeah, basically if all of the frames or the graphs have been built, we're able to just say, prepare the frame, send that to the renderer, everyone's happy. So that took care of 3 of those things. The runtime, because the runtime is now just the Tokyo runtime. We've got asset loading, which is happening within the graphs. And those graphs are basically just calling out asset loader, grabbing things in their own little thread, because that's what's happening when the graph gets built. And the graphs for the events have also been completely multi-threaded now because they're just tasks or futures that have been spawned onto the Tokyo runtime. But we still have our rendering, we still have our phase tracking, we still have our decoding to do. So the next step was the render thread. We were using Vulkan, like I said. So basically we had our Vulkan renderer at the time that was running in its own little thread, pretty much from the beginning. I don't actually think this was part of the main part, but I wanted to talk about it because it's cool. What we do is we just build this Vulkan renderer. So we grab the device from Android or iOS. It just gives us either a UI frame, or I think the Android one is just a system or something along those lines. Pop that into the Vulkan renderer, build everything up, and then we just send a little thread through to the renderer. And basically we've just got a sync sender across the loop, which over here in the rendering frame. So this is the actual render loop. I've obviously minified it down a little bit. You don't want to read that code that I wrote. Just receives a message across from the sender, which gets submitted from all these other draw calls. And then we just match those per frame, render out with the correct shaders, correct vertices, everything along those fun little buffer things. And basically, once we hit the present render command across the thread, we break the frame, we then render it with all the rest of the code that you don't want to see. And we now have rendering happening pretty simply. Obviously, it wasn't simple back then, but it works now, so who cares? So there, yeah, rendering's done. We don't have to think about that anymore. Good times. The next up was face tracking. So face tracking, Nathaniel spent a long time with this one. It's based off a fair few things, but the main part that we kind of took and built upon was Pico, which is a C library. Don't ask me what the acronym stands for. I hate acronyms. And basically, we refactored this to include threading from within C. So we actually did part of the threading in C, and the graph would then call out to these libraries as the event was happening. So it's grabbing camera data, it's calling off to the C library Pico to basically detect the face after it's learnt everything about faces at the time. And then it throws it back to the Rust code with basically, it just tells us where it thinks a face is. We take that data, we go, yeah, I'm sure it's fine. And we put that into the graph and everyone's happy. Basically, this C library was, I think, changed about 8 times, 9 times, something along those lines. Basically, at one point, it wasn't working on certain phones. Then we had to make it faster. Then at one point, I think it was running too fast in a loop. So we had to fix that. And then, yeah, a lot of things happened. I don't talk about C. Moving on. So now we have face tracking completely multi-threaded. We don't have to worry about that either. But the next step, and this is the part I had the most to do with at the time, especially on Android, was decoding video and audio. So I'm going to talk about this all night. So we could have used something like CPAL, which is a cross-platform audio library that would allow us to just run everything as seen fit, throw a WAV file in there, everyone's happy. But there's no such thing for video. We can't just throw FFmpeg into this. Doesn't get hardware rendering or hardware decoding or encoding, so we'd be shit out of luck in that regard. But because we're using Android and iOS, they both have media decoders built in that are hardware decoders and encoders, but they're not in Rust. So we have to go with foreign function interfaces. We're calling into C, it's going to be fun. Thankfully, it wasn't too crazy. Basically, all we had to do was actually just build the media decoder as its own little Rust type. And this was a lot of abstraction around the Android code that honestly the documentation wasn't quite correct. Don't get me started on the iOS documentation if you want to talk documentation. So we build the media decoder and we just throw it on the CPU pool. It worked. Everything was fine. But what we noticed was it was actually running too quickly. So one of the problems, you'll see it down here, I've got a little sleep down here to actually slow the loop down because it was eating absolutely everything running about the application. We noticed that as soon as it started rendering a video, everything just came to a standstill. Couldn't figure out what it was, and then we saw this thread was somehow utilizing the entire of the CPU on an Android phone. I went, it'll be fine, and just added in that little sleep. I think we ended up changing this pretty quickly because who would trust that code? And we put in something that actually looks at decoders and looks at how many frames have been buffered and goes from there to make sure that it's not overloading the cores, but is doing something at the same time. But basically all we had to do was build this FFI interface around the actual native encoders and decoders. That took quite a while, especially since in the beginning I had no idea what FFI was. So that was a good start. And then we slowly moved to me becoming more understanding of what FFI is. And eventually it became a nice unsafe object, but the unsafe object was able to do things correctly. So that's all that mattered. That's where the unsafe implementations of send and sync came in as well, because it doesn't know what this pointer is that I'm saying exists and will be fine. You just throw an unsafe implementation of send and sync, everything's fine. It all works. So everyone's happy. And yeah, pretty much all this does is runs in a thread on its own, in a loop, constantly grabbing the next frame if it can. If it can't, it'll sleep for a little bit. Everyone's happy. So that's basically how the media decoders worked for both video and audio, because we needed hardware as much as we could because software was just going to be way too slow. And basically this let us have video and audio decoded and encoded on Android and iOS. We had a pretty smart system of how we share those around, but I'm not going to go into that because I don't even know how it works properly. So we now have everything multi-threaded. Everyone's happy. And we had 0 issues by the end of it. No, we didn't have 0 issues. We had 1 issue. It was running too quickly. So we had to add in a thing called a timer. I'm sure you've heard of it. The timer actually had to slow the runtime down quite a bit because things were happening in, I think we got it down to like 9 milliseconds on a decent-ish phone. And well, we were targeting 40. So things were running pretty quickly. I'm sure the kids wouldn't have been happy if hot potatoes ran in about a quarter of the time it normally does. So yeah, we had to add in a little time checker to make sure everything would run nicely, and that all worked out seemingly well. It's still going. It's still in apps today. The CTO of our company's daughter is actually the biggest user of the thing. The problem there is she gets it for free, so our client gets no money from it, unfortunately. So that was quite hilarious, and he's still kicking himself in the ass for that one. Basically, that's everything. It was a wild 1 week. Nathaniel in a hospital bed, us just watching code come in occasionally, and yeah, then me trying to throw my spin of what Rust could be onto it. So yeah, thank you very much for listening. And if there's any questions, please. Oh, and if I got anything wrong, please don't tell me to correct it. No. The compiler tells me what goes wrong, I'm fine.
I've got the microphone, so
yeah,
I might as well go first.
Go for it.
So since the operation and everything went well, has the code changed to wake up the thread from sleep and actually, give it some work to do rather than wait?
Yes. So eventually it got to the point where I think James came through and was like, yeah, this isn't going to fly. And what he did was he actually made it look at the queue of how many frames had been buffered ahead of time. And it was pretty smart in regards that it wouldn't let too many things buffer, but it also wouldn't let too few things sit in the buffer. Because we noticed that the Android media decoder actually sometimes had a few issues where it would, for some frames, especially when it's not dealing with iframes, if anyone knows what iframes are, they're basically the core frame of MP4 or pretty much any codec. And then you have your intermediate frames in between that aren't your key frames. When it was decoding a keyframe, it could take anywhere from 20 to 40 milliseconds, on some old phones. And we were dealing with some wild Androids. So in that case, you wanted to keep the queue ahead quite a bit in regard to that, because you don't want to have the queue be empty and then all of a sudden you're waiting 40 seconds for your frame to actually be decoded, let alone rendered to the screen or prepared. So I think what ended up happening, I haven't looked at the code in a while, and I was on an old commit because I wanted to be fresh where Nathaniel left it after a week. And what we ended up doing was we basically just set a hard limit of the maximum amount we'd keep in the queue, the minimum amount we'd keep in the queue, and we just keep it in between that. And basically, if it noticed the queue was fine, we just kicked it off. But if the queue was emptying, we'd speed it up and set it back to going again.
That's what was the interface that you use for image processing to getting?
For the image processing, are you talking about when we're getting it out of videos or something else?
Yeah.
Out of videos?
Not the decoding. I mean,
oh, yeah. So from the decoder loop, how we got those images to screen, basically. So what we found from the Android media decoder and the iOS one was slightly different. It was coming out as YUV 420 planar format. So basically just what you'd pretty much expect a graphics card to throw you, as this was running on hardware. And what we were getting was those YUV frames. And then we would take those YUV frames, and I'm pretty sure we were converting them to RGB in a shader to then render them onto screen. James or Nathaniel, you might have a better clue on this one. I think that's what we were doing, right? No? I'm wrong. Good. Was it straight planar image onto the screen? Yeah. There you go. So it was straight YUV from the decoder straight onto screen. I thought there was an RGB step. It is? There you go. Yeah. Yeah. So yeah, the Pico stuff was running on the Luma channel. So pretty much all we had to do was pass through the Luma channel, run through that, and we're able to pretty much take it straight from the decoder into the renderer, except for some Samsung devices, which James had a good time with, where James had to quite literally bit wrangle the decoder because I believe they had U and V mixed up. No. Oh, what was it again? So yeah. Come grab my mic. James was here.
So on Samsung devices, when you get the frame from the hardware on certain Samsung devices, that is uncached. So if you read byte by byte by byte, because it's a Luma field, you'll be getting a cache miss on every single byte you read. So for Samsung devices, we had to have a very specific like SIMD custom implementation, which was also in Rust, that read as much as it could per thing, because like, yeah, getting a cache miss per byte is ridiculous.
Yeah.
But Rust was actually really good with that because I didn't actually have to write any assembly or any SIMD code because the Rust compiler automatically output, what would it be on ARM? It automatically output SIMD code from my loops. Yeah, so that was actually a really good auto vectorization thing in the Rust compiler.
Yeah. Thank you, James. But yeah, also Nick, who is an ex-employee of Tubles, I see, he actually wrote a nice article on auto vectorization in Rust. If you want that, I can link it. I don't mind. I'll ruin your server. Yeah, does that answer your question? Perfect. Any other questions? Yes? Who's got it?
I was just wondering what the ongoing maintenance is like. Do you have to jump in afterwards?
That is not a question for me. That is an unfortunate question for Nathaniel and James. They're the last people that basically committed into the repo. Do you want to talk about that, Nathaniel?
So the question was about ongoing maintenance. Yeah, so this project definitely is a thing that comes back and goes away for a while, then comes back with more features. It's fine. It's what you do for your job.
But yeah, it's still running on Rust 1.53. We haven't moved up the compiler or anything like that. So we haven't had any maintenance around the actual language. It's mostly just been iOS changes something, we have to go in and fix it. Android changes something, we have to go in and fix it.
Yeah, most of the breakage has been iOS version updates. Invariably introduced bugs or just broken something.
Yeah, like last year they broke transparency. That was good fun where we randomly just had triangles all over the screen whenever there was a transparent layer because they changed the way that images were built with metal. So we had to do something about that. So I jumped in and just did it by hand and everything worked out fine. And it didn't even add any complexity to the app. Actually made less lines of code. So that was a nice one. So yeah, there's definitely management in that regard, but it's mostly coming from external vendors, in this case, iOS and Android. But I haven't really hit any Android things besides James's crazy Samsung stuff. But yeah, cache misses. Was there any other questions? Doesn't even have to be about Rust, could just be in general, Tubles. What's going on in the current political, socio-economic state? Hey!
Sorry, I got the mic now. I've got a question.
Hi, Nick.
Hello. This is something I do. Was there any issues with actually having to slow it down more? Did you have any complaints about getting too hot, using up too much battery?
That was one of the things with the media decoder, especially. Even with that sleep in, it still wasn't great because if we had a very fast decoding phone, we'd actually find that it would still fill the buffer up. So we did end up having a buffer amount that we could limit it to. Another thing was, I think the GPU on some phones was having a real struggle with doing all of this at once because we were rendering using Vulkan. So we were stealing a part of the actual GPU in these devices to pretty much have our render system. We're also using hardware decoding as a result. So that's somewhere on the GPU or an inbuilt system. Battery life was a pretty big issue for a while, especially on the more annoying Android devices. The older ones that barely ran anything really. Like I think the Oppo phone was really bad for it. If you ran Hot Potato for 2 minutes, I think you lost about 6% battery life. just like that. It was incredible. And hot potato was like a minute 50. I remember that one. So yeah, 6% battery just like that, just because it had to do so many things at once. So Android was not happy about that, especially utilizing the GPU as much as we did. Yeah. Thanks for that question, Nick.
I was just curious, you mentioned the app uses a Vulkan for rendering, but you mentioned Metal as well for iPhones. So
Yes.
did you use a translation layer or?
We did. So we used Molten VK. At the time, I don't think it was bought out by Steam just yet, but it did eventually get bought out by Steam in the interim. So what we were able to do is pretty much just keep our Vulkan code, include the Molten VK stuff, and it kind of just worked. I don't think we actually had many issues regarding rendering as a result of that, besides some issues recently, I think, where we had to start triple buffering. Was it, James? Yeah, we had to start triple buffering because something changed in the Metal side, and Molten VK thought it was doing everything correctly, but Metal thought it was doing something wrong. There you go. Double buffering broke on iOS, and we started triple buffering, and everything was just fine. Yeah. So so we were using Molten VK as that layer, and I don't think we had major issues with it. Oh no, we did. When we tried to admit it to the Apple store, they shit their pants. They were not happy about it. They were talking about all sorts of third-party libs that they didn't support or were going to pull. And then Nick did some magic, and it just worked. So I wasn't there for that. Yeah, you don't remember the dilib stuff that you? I remember you did something around the dilib. No, I think it was something to do with we had to add an extra permission to our app store push. But yeah, it was just a linker problem. Oh, okay. There you go. I was very far away from that. But yeah, it was a linker issue then. But yeah, we used Molten VK. Thankfully, that went open source. Otherwise, it would have cost us a lot, but things happen. Perfect. Oh, that's right. Yeah. We couldn't use the official one. We had to go back to the AOSP one. Yeah. Yeah. Things happen. Software's weird. Hardware's weirder. So yeah. All right, no more questions. Perfect. Hardware is weird. Now I'm going to pass it. Thank you.